Welcome to our presentation on enemy character aging by Ahmed Wael and Adham Khalid Higazi. This is the table of contents, and we will go into the presentation. First, the problem statement. We want to create a model that ages teen enemy characters into seniors and also de-ages seniors back into teens. This is a sample of the expected input and output in the two cases that we have. And our motivation is to learn about GANs, get hands-on experience in the full machine learning cycle, including data collection and data cleaning and so on, being pioneers, and this will come in later, and just having fun with the domain. To summarize our proposal very briefly, GANs are networks that generate fake data. These are data from this person does not exist. There are two networks, a generative network and discriminative network. A generative network creates fake data, and the discriminative network tries to separate or identify the real data from the fake data, and the two networks kind of compete with each other. These are the data sets that we initially looked at, and the one at the very right-hand side is the one that we are going to be using. Its main benefit compared to others is that it is labeled. We are able to identify the seniors from the teens from the get-go. We have some sort of ground truth that is relevant for ourselves, for the pipeline. The problem is that it had to be scraped, but we managed that. Let's look at the evaluation metrics that we discussed in the proposal. Visual examination remains to be very popular despite being time expensive and non-objective, and there are other variations in it that use crowdsourcing. Average log likelihood was introduced by Ingood in 2014, however, it is considered outdated today. Inception score is based on the pre-trained model Inception version 3. It was introduced in 2016, and it measures image quality and image diversity, and it is a popular metric. Another popular metric is the Frechet inception distance, also based on the same pre-trained model, Inception version 3, and it measures the similarity between features vectors of two groups of images, the real and generated. And yes, it is also a very popular metric. Adam will now walk you through the related works.
So we believe that we are the pioneers of this particular problem, as we, in our research, we did not find papers that tackle this problem particularly. However, we took inspirations of multiple image-to-image scans, which specifically models that tackle the problem of human aging and de-aging, and also worked with unpaired datasets. The first paper, we were mainly inspired by three papers. The first of it was the phage aging and with identity preserved conditional generative adversarial networks, which worked on unpaired datasets, meaning that we should not have two images of the same human. However, we should give it a lot of senior humans and a lot of teen or young humans, and it will automatically learn it. Also, we took inspirations of unpaired human image to image translation using cycle consistent adversarial networks, which worked on unpaired dataset. However, it did not work for human aging and de-aging. Our main paper that we based our model on is the implementing cycle GAN for age conversion, which both worked on unpaired datasets and worked for human aging and de-aging, which is a similar problem to our domain. The different architecture of the cycle GAN allowed that some flexibility, such that it translates images from domain A to domain B. In this diagram, domain A here is the horse, and domain B horses, and domain B here is zebras, such that it translates the domain A, the horses, by the first generator X to Y to zebras, and then it passes to the discriminator to calculate the GAN loss. And then it also it has another generator which generates back from Y to X, mapping the domain B back to its original form in domain A, and then it calculates another loss of the cycle consistency loss, which compares both the original image and the reconstructed image of that same domain to make sure that it's still having the same essence of the original domain, while also passing the unique characteristics of the another domain by the other discriminator of Y. So this can be mapped back to our domain problem, which is human aging and de-aging. As you can see here, the original images of a young man can be aged and then translated and then reconstructed back to its original form, and the same and vice versa on the original, where it can go back to a younger version and then reconstructed back to the more aged version. So our proposed solution to our problem, it's a similar problem. However, we would face a lot of challenges that we need to tackle in order to translate it to anime characters. First of all, is obtaining a labeled data set using a lot of scraping techniques. And we need to clean this data since a lot of it would come of irregular forms and that would confuse the data, the model. And then we also need to do data augmentation in order to increase our data set. And of course, we need to do some model modifications, hyperparameter tuning in order to make it work properly for the tweaked domain of enemy characters. And also the nature of the domain itself is that enemy characters sometimes have difference in their appearance, which would also confuse the model. So our progress and reports that we did for this milestone, we did first we did scraping and then cropper, and then we did our maze model and model variations, which we'll all discuss briefly next. First of all, the scraping, we found first we found the scraper that we had to have that we had to modify heavily in order to improve its efficiency since it was originally so slow. And then we scraped scraped the label images that we mentioned from the website we mentioned before into two categories, teen and senior, which our model needed as an input. Then we passed it by a cropper in order to crop particularly the faces of the enemy, since the characters since the pictures were not only faces. However, the original cropper did not work properly, so we had to find another cropper to work properly, specifically with the senior images, since it did not capture its faces properly. Our base model, which was based on the paper that I mentioned before, which had the teen characters as its domain A, and then the senior character as its domain B, and we ran it on multiple iterations. First one was 5 epochs on 160 senior images and 1,200 teen images. Then we did 18 epochs on the same dataset, but then we, with another cropper, we had the chance to give more senior images of 800 images and 2,000 teen images with 15 epochs. This resulted in some of the pictures that you see here. As you can see, the model might learn some characteristics such that it takes the young anime character and maybe makes the hair whiter as an aged characteristics, and vice versa on the original on the aged character, and tries to make it a little bit younger, so it makes the hair darker. And this can show you that the model is learning some characteristics. However, of course, it's a little bit confused. So as you can see, there are some confused behavior. However, that will be fixed later with more hyperparameter tuning and later iterations. Ahmed now will take you through the model variations that we did.
And now for the model variations, we simply have to go through what we changed in the base model. It had the input image size 256 by 256, batch size 2, and the teen data set was only 1,200 images. In the upcoming variations, we were able to increase the teen data size to 10,000 images by just running the scraper on more pages. We varied the batch sizes to 8, 16, and 32, and we varied the input image size to 64 by 64 and 128 by 128. These are some of the results. These are 64 by 64. They were not really promising, so we then moved to the 128 by 128, and the results were much better. The reconstructing of the image specifically is noticeably good. However, the translation needs some improvement, as the faces do not look younger or older than they do, or not noticeably so. The next steps that we have to do, obviously, first is hyperparameter tuning. We need to perfect our model to the best of our ability. We need to do data augmentation, seeing as the senior data set, even at 800 images, is very small. So we need to increase that through translation, brightness control, so on and so forth. And we need to save and load the model correctly in order to have more efficient ability to train the model with a very large number of epochs without Google Colab running out of GPUs, for example. Thank you for our slide. Thank you for listening to our presentation, and arigato.
Arigato.